First, thanks to Edith and Michel for this amazing conference. Today I will present a model of supernova expansion in the Milky Way. So, first, why do we care about supernova remnants? So you may know that supernova remnants are drivers of turbulence in our galaxies. They can also regulate the star formation, and they can be accelerators of cosmic rays. You also may know that there is a strong thermochemical impact on the supernova remnants, because they are making the transition between the warm neutral medium into the cold neutral medium. But there is also one point that most of the time we forgot, is the kinetic impact of the supernova remnants. And what do I mean by kinetic impact? I mean the ionization due to the radiation or the shock of the supernova remnants. And more than that, why do we care about supernova remnants? Because we miss all the supernova remnants. What do I mean by old? I will explain that later, but just to say that we only found, Benjamin, only found the only tracer of all supernova remnants, which is the high pressure carbon, and it's from only 1 year. So we are really missing to a tracer of all supernova remnants. Okay, so my model is named Skynet, so supernova kinetic yield on galactic emission tracer. You may recognize the logo, but at least this model there's two submodels in that model, a galactic model and a supernova model. So let's first introduce the galactic model. So this model is quite easy. It starts from order of magnitude, so the mass of the supernova remnants, its energy, then the shape of our galaxy, so from Valley 2022, so 4 equal arms, spiral arms with their pitch angle, then the rate of supernova remnants in our galaxy, and the different type of supernova remnants that we can see. There is also the density radial distribution, which is extracts from Elia work and Mark-Anton Navigation work, and we also consider the flaring of our galaxy. So just to show you a top view of our galaxy, so it's maybe hard to see, but this is in kiloparsecs, okay? So this is our galaxy from top. Each point is a supernova remnant. Okay, we only consider supernova remnants in which the velocity is between 30 and almost 200 km per second. And so each point is at scale. This is at scale. So you can see that there is plenty of them, around 10,000 supernova remnants in our galaxy. And just to have a few more information about our distributions, here we have the density distribution. Okay, so you can see that there is a big bump because of the start of the spiral arms. And you also have the flaring, okay, around our galaxy. You can see that there is much more supernova remnants in the dense region. Okay, so then this is it was a top view of our galaxy. Now it's a slice view of our galaxy. So we are looking at our galaxy from Earth. So we are looking at the galactic center. So this is in degree, not in kiloparsec anymore, but at least we are looking at the right center of our galaxy between -5 degree and +5 degree. Still same scale of velocity. Each bubble is a supernova and is color dependent velocity. I just remove all the slow, not the same slow as here, because to me, what you call fast shocks are to me slow shocks, but let's say that below 50 km per second. Okay, so you can see that there is plenty of them. And just to be a bit more precise, here you have the number of supernova remnants that you can see, depending on the galactic longitude you are looking at. So we are on the galactic plane, latitude near, and you can see that even at super high scales, super high degrees, I mean like on the opposites of the galaxy, you can still see quite a few supernova remnants. And you can see that you can see 10 of them when you are looking at the galactic center. So it means that you can't, if you're looking on the galactic plane, you should see supernova remnants, and plenty of them if you're looking on the right direction. So it was a galactic model. Now have a look on the supernova model. So I will just first make a quick recap of what is a supernova remnant. So just the matter expelled and swept by the star explosion, and we will distinguish 3 main phases during the evolution of supernova remnants. So the first phase, the pre-expansion phase, during that phase the shock front is not slowing down, it conserves its velocity, because the matter expelled is much more massive than the matter swept. Then you have the second phase, in which the 2 phases are almost as massive as the other, so the shock will start to slow down, but won't be yet able to radiate. So it won't really cool down, it will only slow down. And then you have the last phase, in which the shock will start to really cool down and continue to slow down. So this is what I call all supernova remnants, that guy, this is all supernova remnants, And I may pick your attention on the time scale. So the first phase is only 400 years, the second one is 50 kiloyears, and the last one is 1 million years. Which means that 95% of the lifetime of a supernova remnant is during that third phase. Okay, so, okay, we only care about the old guy. So just to say, we are only modeling the third phase. I will explain why later, but just to mention it's 95% of the lifetime, so not that bad. And just to give you the names that we used, so, okay, the shock front, we know what is the shock front, but the matter which is not yet shocked is known as the pre-shock, and the matter which has been already shocked is the post-shock. Quite easy. And then we add something, which is the hot bubble. What is the hot bubble? It's the two previous phases. As I mentioned, they have been shocked, heated up, but we aren't able to cool down. So they will cool down during the third phase. And that's the impact of their cool down that you will be able to see in that third phase. So the matter have been shocked earlier, but will cool down in another phase. So that's what we will model for the hot bubble. Just to give you an example, you have three curves of the cooling of the hot bubble depending on the density of the external medium. And so you can see that it will cool down in a few tens of kiloyears. So that's the typical time when the third phase will start. Okay. Okay, so just I will now speak about the shock model we are using. So it's named per shock code. So as Pierre explained already, it's a 1D MHD shock code. It's at steady state, and this is a key point. Because we are steady state, we can't properly model the first and second phase, because I'm not able to cool down. That's why we are only modeling the third phase and the hot bubble, because it's only what could the per shock code do. We are obviously out of equilibrium, and we are considering that the magnetic field is transverse to the velocity. Okay, it's a multi-field code. And just to mention, as you may have seen with the spectrum of Pierre earlier, there is many lines. And when I say many lines, it's almost 1 million lines, thanks to the KMT database. We are solving an exact radiative transfer, and all the atoms are considered up to iron. So thanks to all those parameters, we are able to follow the dynamic, the thermic, thermal, and chemical evolution of the shocks. And the shock is iterative, but if you do have questions, I will explain that later. Oh, never. So just to mention, I will use that kind of plot quite a few times. So always the left plot is the pre-shock, the right plot is the post-shock, and in between it's the shock front. Just to mention, so those are distances in centimeters. Okay, just to mention that the pre-shock is always much larger than the pre-shock. Okay, so first we have a look on the density. So the density is the purple line. You can see that it's one neutral medium, which is becoming cold neutral medium, so it's densified. And you can see that at the end we are reaching between 10 and 100 particles per centimeter squared, just to then you have the information. And then if we look at the temperature, you can see that there is a bump on the material which is not yet shocked. This is because the shock front is very hot, and this hot shock front with radiates emit X-ray, and this X-ray will be able to ionize or heat the materials, and so we will see a bump, that's what we call a radiative precursor. And obviously, then the material is shocked, and then it will be heated up and then cool down slowly.
So, sorry, it seems strange that your gradients are in the post-shock region and not on the front.
Yeah, okay.
Probably you can explain.
Yeah, so it's just the viscous length.
Ah.
It's just like, this is super small. It's like, so, because those are log scales, I could have removed them and just like mask it, but it's just to be fair, this is just the viscous length. Okay, so now you have seen the galactic model, you have seen the supernova model, then combine both of them to see the emission of supernova remnant in our galaxy. So first we will look for N+. Why do we care about N+? First, because N+ crosses fully ionized region, quite hard to ionize, harder than hydrogen. And then we also have measurements done by Herschel in 2015, which show that using the ratio of the lines, we can see that the electron density is between 10 and 100, which is the typical density of the post-shock. So we may guess that those emissions are coming from the post-shock of supernova remnants. And I can show you, okay, those are the values between 10 and 100 particles per centimeter cube, which means that we are maybe seeing supernova remnants. So first, this is the same kind of shock, and here we are looking at the evolution of nitrogen for what I call a slow shocks, 50 km per second. Okay, and you can see that in the pre-shock, there is quite a few N plus created because of the shock front, but not that much. Mostly the N plus is made in the post-shock because of the collision of the shock front. It's completely different if you are looking at faster shock, so a twice faster shock, 100 km per second. Then you can see that the shock front is so hot that it fully ionizes nitrogen, and even more than that, create N2+. So it can also create, you can see a small peak of N+, so a part of the N+ is created in the pre-shock, but most of them is created in the post-shock. So the N2+ will be heated up after that and will even create N3+, and then this N3+ will recombine into N2+, 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 etc. And this is how we will create the N+ in those fast shocks. Just to say that there is quite a few different ways to create N+ in a shock, depending on its velocity. Okay, so this is the results. So we just like run our modelization, average it on like 100 galactic distribution, and what you can see is the column density depending on the longitude. So you can see it's quite flat, then you're entering in the spiral arms, so that's why you get the bumps, and then we have a plateau in the center of the galaxy. So those are the two lines seen, the two first level of N+. And if you want to compare with data, we have those measurements from Cargèse, so 2 N+ lines in infrared. It's just a galactic survey of the N+. And so those are the points that you can see. So many points, many upper limits. But at least what you can see that we are somehow following the same shape. And more than that, we have a good ratio between the two lines compared to the two lines that are measured. Even if we are not fully retracing the N+, we are only modeling 15% of what is emitted, but at least we have the good ratio and the good shape of simulation. So, last slide, just to say that, so we have seen that N+ could partly trace from our remnants. We can't fully explain the N+ which is observed, at least a part of it, and at least its ratio. Skynet is still a toy model, but the N+ results are quite consistent when you are changing the galactic parameters, sorry. And that I only showed 2 lines of N+. Obviously, there is millions of lines, so it could be great to see if we can find new traces of all supernova remnants in our galaxy. And more than that, now we need to take into account the SNR if you want to modelize the Milky Way ionization.
Thank you.